Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of scientific discovery, few experiments resonate with the profound simplicity and revolutionary impact of Ernest Rutherford's 1911 investigation into the structure of the atom. This pivotal work, published under the unassuming title The Structure of the Atom, did more than refine existing theories, it shattered them. It ushered in the nuclear age, forever altering humanity's comprehension of matter's fundamental building blocks. Before Rutherford's groundbreaking study, the prevailing atomic model, championed by J.J. Thomson, envisioned the atom as a plum pudding, a sphere of uniform positive charge embedded with negatively charged electrons, akin to plums dispersed throughout a pudding. This model, while offering a semblance of explanation for atomic neutrality, proved utterly inadequate in the face of emerging experimental evidence, particularly the perplexing phenomenon of alpha particle scattering. Thomson's depiction of the atom struggled to account for the observed behavior of alpha particles directed at thin metallic films. According to his model, these relatively massive, positively charged particles should have passed through the diffuse positive charge of the atom with minimal deflection, experiencing only slight deviations from their original trajectories. The positive charge, theorized as uniform across the atom, produced minimal electrical effects on the trajectory of the alpha particles. The experimental reality, however, painted a drastically different picture. A team led by Rutherford, including Hans Geiger and Ernest Marsden, meticulously bombarded a thin gold foil with alpha particles emitted from a radioactive source, specifically radium. They then scrutinized the resultant scattering patterns using a zinc sulfide screen detector, a device that emits a flash of light upon impact from an alpha particle. The results proved astonishing, and in many ways counterintuitive. While the majority of alpha particles did indeed pass through the gold foil with meager deviations, a disconcertingly substantial fraction, approximately 1 in 8,000, experienced deflections at angles exceeding 90 degrees, some even backscattered, rebounding almost directly towards the source. Such a startling outcome flew in the face of predictions based on the plum pudding model, which suggested that their alpha particles would experience minimal disturbance on their trajectories. Rutherford himself is quoted as saying that the results were as incredible as if you fired a 50-inch shell at a piece of tissue paper, and it came back and hit. The experimental apparatus itself comprised several key components, each designed for precision and accuracy. The alpha particle source, radium, provided a steady stream of positively charged projectiles. These particles, possessing significant kinetic energy, were directed towards the heart of the experiment, the thin gold foil. The choice of gold was strategic, owing to its malleability, which enabled the creation of extremely thin, uniform sheets, minimizing the possibility of multiple scattering events within the foil itself. Surrounding the gold foil was the zinc sulfide screen, a crucial element instrumental in detecting the scattered alpha particles. When an alpha particle struck the screen, it generated a minute flash of light, detectable through a microscope. By meticulously recording the number and angular distribution of these interlations, the researchers were able to map the scattering patterns with considerable accuracy. Initially, Rutherford posited that the alpha particles might experience multiple, minor deflections as they traversed the atoms within the gold foil, collectively compounding to produce the occasional large-angle scattering events. However, calculations based on this hypothesis revealed that the probability of such cumulative deflections accounting for the observed frequency of large-angle scattering was astronomically small. Furthermore, the sharp, well-defined nature of the scattering angles suggested a single, powerful interaction rather than a series of weaker ones. The experimental evidence stood in stark contradiction to Rutherford's initial assumption, thus compelling him to reconsider the very structure of the atom. The observed backscattering, in particular, posed an insuperable obstacle for the plum pudding model. It was virtually improbable, based on Thomson's assumptions, for an alpha particle to encounter a force strong enough to reverse its direction within the confines of the atom. Rutherford, grappling with these incongruities, formulated a radical alternative, the nuclear model of the atom. This model proposed that the majority of an atom's mass, along with all of its positive charge, resided in a minute, dense core at the atom's center, termed the nucleus. The negatively charged electrons, conversely, were imagined to orbit this nucleus at a considerable distance, akin to planets revolving around a star. This model, while seemingly simple, held the key to explaining the enigmatic scattering patterns observed in the gold foil experiment. The rare instances of large-angle scattering, Rutherford reasoned, resulted from alpha particles passing in close proximity to the positively charged nucleus, experiencing a powerful Coulomb repulsion that deflected them sharply from their original trajectories. The more common small-angle deflections arose from alpha particles passing farther from the nucleus, encountering weaker repulsive forces. This essay will explore the intricacies of the gold foil experiment, dissecting Rutherford's interpretation of the experimental results. This includes examination of the development of the nuclear model. It will also discuss its profound implications for our comprehension of matter, in tracing the evolution of atomic theory. From the indistinct vision of Thomson to the precise model of Rutherford, modern physics begins to truly emerge. In 1911, Ernest Rutherford presented his groundbreaking model of atomic structure, forever altering our understanding of matter. This model arose directly from his interpretation of the infamous gold foil experiment conducted in his laboratory at the University of Manchester. Prior to Rutherford's work, the prevailing atomic model, proposed by J.J. Thomson, envisioned the atom as a plum pudding, a diffuse sphere of positive charge with negatively charged electrons embedded within. Rutherford and his team, Hans Geiger and Ernest Marsden, designed an experiment to test this hypothesis by firing alpha particles, positively charged helium nuclei, at a thin gold foil. Classical physics predicted that the alpha particles should pass through the foil with minimal deflection. However, the experimental results defied these expectations. While the majority of alpha particles did indeed pass straight through the gold foil or experienced small deflections, a small but significant fraction, approximately 1 in 8,000, were deflected at large angles, some even bouncing backward. Rutherford famously remarked that this observation was almost as incredible as if you fired a 15 shell at a piece of tissue paper and it came back and hit you. This unexpected result challenged the Thomson model and prompted Rutherford to propose a radically different picture of the atom. Rutherford's interpretation of the gold foil experiment led him to postulate that the atom consists of a tiny, dense, positively charged nucleus at its center, surrounded by orbiting electrons. The nucleus contains almost all of the atom's mass, while the electrons occupy a vast, mostly empty space around it. This model explained the observed scattering patterns. Most alpha particles pass through the empty space unaffected, while the rare large angle deflections occur when an alpha particle approaches close to the nucleus, experiencing a powerful Coulomb repulsion. To quantitatively describe the alpha particle scattering, Rutherford developed a mathematical model based on the Coulomb force between the alpha particle and the nucleus. This model assumes that the alpha particle and the nucleus are both point charges, and that the interaction between them is purely electrostatic. Using classical mechanics, Rutherford derived a formula for the angular distribution of scattered alpha particles, known as the Rutherford scattering formula. The Rutherford scattering formula predicts that the number of alpha particles scattered at a given angle is inversely proportional to the sine to the fourth power of half the scattering angle. This formula accurately matched the experimental data obtained from the gold foil experiment, providing strong support for Rutherford's nuclear model. The quantitative agreement between the theoretical predictions and experimental results was a crucial validation of the model's accuracy and predictive. Rutherford's model possessed significant strengths. It successfully explained the alpha particle scattering data and provided a clear framework for understanding atomic structure. The model also suggested that the positive charge and mass of the atom are concentrated in a tiny nucleus, leading to the concept of nuclear reactions and the possibility of transforming one element into another. This marked a profound shift in scientific thinking, moving away from the idea of the atom as an indivisible entity and opening the door to the exploration of its internal structure. The nuclear model, elegant in its simplicity, also faced significant weaknesses. According to classical electrodynamics, an electron accelerating around the nucleus should emit electromagnetic radiation, losing energy and spiraling into the nucleus. This would render the atom unstable, contradicting the observed stability of matter. This issue, a major problem, threatened the viability of Rutherford's model and stumped physicists. This instability problem was addressed by Niels Bohr, who built upon Rutherford's model by introducing the concept of quantized energy levels. Bohr proposed that electrons could only occupy specific orbits with discrete energy levels, preventing them from continuously radiating energy and spiraling into the nucleus. Bohr's model, while still retaining the basic Rutherfordian structure, incorporated quantum mechanical principles to resolve the instability issue and provide a more complete picture of the atom. Rutherford's nuclear model had an immediate and profound impact on atomic physics. It shifted the scientific paradigm, replacing the plum pudding model with a more accurate representation of the atom as a nucleus surrounded by orbiting electrons. This model provided the foundation for future developments in nuclear physics, including the discovery of the proton by Rutherford himself in 1919. and the neutron by James Chadwick in 1932. These discoveries further refined our understanding of the nucleus and its constituents. The impact of Rutherford's work extends far beyond atomic physics. It laid the groundwork for the development of nuclear energy, nuclear medicine, and various other technologies that rely on our understanding of the atom. The gold foil experiment remains a classic example of scientific inquiry, demonstrating how careful experimentation and insightful interpretation can lead to revolutionary discoveries. It continues to be used as a teaching tool to illustrate the principles of atomic structure and the scientific method, reflecting on Rutherford's 1911 model. Its profound impact on the understanding of atomic structure stands clear. It stands as a cornerstone of modern physics. The enduring relevance of the gold foil experiment lies both in its elegant design and in its role as a tangible demonstration of scientific progress. The philosophical implications of the nuclear model, its departure from classical physics, and its contribution to quantum mechanics mark a turning point in our comprehension of the universe. The influence of Rutherford's work on later experimentalists, such as Chadwick, and theorists, such as Bohr, as well as its lasting impact, secures his legacy as one of the greatest scientists of the 20th century.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.